Hi, everybody. This morning I want to go over the theory behind the photoelectric effect experiment that we're about to go through. Okay? I should mention, everything we're going to talk about now is also covered in the lab handout. Now, let's switch over to the iPad to go through the theory. Let's start with this cartoon picture of the photoelectric effect experiment. Light is incident on a metal surface, and under some conditions, electrons are emitted from the surface, photoelectrons. Okay? Einstein's model of the photoelectric effect assumes that the energy delivered by the light comes in packets, and the size of a packet is hf, where f is the frequency and h is Planck's constant. And photoelectrons are only emitted if the energy of a packet is larger than the work function of the metal, where the work function is the minimum energy required to remove an electron from the metal and take it away. Very good. And if this condition doesn't hold, then no electrons are emitted. From the point of view of our discussion, it'll be useful to look more closely at this picture. So the electrons in the metal, those are in what are called conduction states. They're bound to the metal, but they can move around within the metal. The electrons that are emitted are in free states. Okay? Now, we can describe this with a second sort of cartoon picture here, which is an energy diagram. That is, the vertical axis in the diagram is energy. Okay? Now, this diagram is a little complicated, but it's worth going through it carefully. So let's go through it now. So first of all, notice that at the bottom of our diagram are the conduction states in the metal. We assume that there are all of these states in the metal, and the electrons, or the valence electrons in the metal, fill up these states up to some maximum energy, called the Fermi energy. That's very simply the modern picture of a metal. Okay? Then there's a range of states of energies over which there are no electrons. And then at still higher energies, we have the free states. So if we give an electron from the metal enough energy, we can promote it into one of these free states. The free states correspond to electrons that are not in the metal anymore. They're just free. They're moving through empty space. Of course, they could be moving through empty space quickly or slowly, and that determines their total energy. So for example, an electron at the lowest possible energy free state would be an electron that's removed from the metal but has no kinetic energy. It's motionless. Electrons that have kinetic energy have additional extra energy. And so higher energy free states correspond to electrons with kinetic energy that are moving faster and faster and faster as the energy goes up. Okay, so now we can see that in this picture, we can only excite a photoelectron with photons that have energies HF greater than the work function. Because the work function is the minimum energy required. That is, it's the energy difference between the lowest energy free state and the highest energy bound state. The energy to take the most energetic electron inside the metal and put it into the lowest energy free state. Now, if we assume that HF is greater than the work function, then our picture will look like the picture over here on the left side of the diagram. If we excite an electron from one of the most energetic states, then it will be left in a free state with some excess energy, okay? And that excess energy will become kinetic energy. Will create an electron in motion. Alternately, we could take an electron from one of the lower energy occupied states in the conduction band and promote it. And that might also give us an electron that has kinetic energy. But as you can see, its energy will be less than the first case. So its kinetic energy will be less than the kinetic energy of an electron excited from the highest energy state. So you can immediately see that the first case, where we take an electron from the highest energy occupied state, is kind of special because those electrons have a kinetic energy which is the maximum possible kinetic energy. Okay? Other electrons could have less kinetic energy, but no electron can have more. Very good. So that's what we want to get from this picture. Here, just to sum up what we found, starting with Einstein's idea that the energy of a photon is given by HF, we can see that the maximum kinetic energy an electron can have is HF minus the work function from energy conservation. Okay, let's stop there.